Hi everyone, it's Mr. Hamilton here. In this video, I'm going to go over a real-world application of sinusoidal functions. What we're about to look at is a flagpole swaying back and forth in the wind. This has similarities to someone swinging on a swing back and forth. It also has similarities to skyscrapers. As wind blows on skyscrapers, they also sway back and forth. So engineers would have to test for these kind of things as well. And it also has similarities to tuning forks. And they vibrate back and forth, creating the sound that we hear. So just because it's a flagpole is swaying back and forth, it's not the only application. There's many other applications. So let's look what the question says. The top of a flagpole sways back and forth in high winds. The top sways 10 centimeters to the right, which is plus 10 centimeters, and 10 centimeters to the left, which is minus 10 centimeters of its rest position. And it goes back and forth 240 times every minute. At t equals 0, the pole was momentarily at its resting position. That doesn't mean it's at rest. That means it's at that position. So it's vibrating past that position right at t equals 0. So then it started to move to the right. Part A says determine the equation of a sinusoidal function that describes the distance that the top of the pole is from its resting position in centimeters compared with time in seconds. So let's have a look and see how we do that. Ultimately, what we have to do is we have to represent something in terms of y equals a times sine or cosine. In this case, I'm going to use a sine function, but it could be cosine as well. A times sine of k x minus d in degrees. I'm going to do this in degrees plus c. And so we need to ultimately determine what each of those variables are. What is a? That's represented by the amplitude. What is k? That is 360 over the period. What is the d value? That is the phase shift. And what is the c value? That is the equation of the axis. So how it is shifted up or down. All right. So what I'm going to do before I do anything else here is I'm going to get a sketch for what this looks like. Because having a diagram always is helpful. So we always want to draw the diagram. So if this is distance from the equilibrium or from the resting position here in centimeters, then this is time in seconds. Now, the first thing I note is that it goes up to positive 10 when it's at the right and negative 10 when it's on the left. So I know it's, if I'm drawing a box for where one period would fit, it's going to go between negative 10 and positive 10. And then the equation of the axis is right here at 0. So we already know what the equation of the axis is. That is its resting position, and so that's going to be c equals 0. Y equals 0 is the equation for that line, so that means c equals 0. So let's go ahead and also determine the amplitude here. We know what that is going to be. So we know that because the amplitude is equal to 10 here, that the absolute value of a, which we'll have determine if it's positive or negative later, is going to be equal to 10. So we're almost there with those two, with the amplitude, or the a value. So now we need to determine the k value and the phase shift. And so that first has to be done by interpreting what this 240 times every minute means. If it's going back and forth 240 times every minute, that means it completes one cycle every 240, or every 240th of a minute. One cycle every 1/240th of a minute. So what we can do is we can say, well, how long is one cycle? So the time for one cycle, or one period, is equal to 1 over 240 times 60 seconds. And so that tells me that one cycle is going to be completed 60 over 240. That ends up being a quarter, or 0.25 seconds. It's only going to take 0.25 seconds for it to go all the way to the right, back to the resting position, all the way to the left, and back to the resting position again. So that means my period is going to be 0.25. So I'm just going to finish my box by putting a 0.25 here. And so if I break that up in half and then into quarters, I'm going to start, it says it started at its resting position at t equals 0, and then it started to move to the right. So it's in its resting position, and it's moving to the right. Moving to the right is the positive direction. That's listed up there. So then it's going to go up to the positive 10, back down to the resting position, down to the negative 10, and then back to its resting position. So it's going to look something like this. There you go. There's the graph. So we almost have everything we need now. Let's just scroll down a little bit and continue working on this question. So what we know is that if it's a sine function, there's no phase shift because it starts at the equation of the axis and goes up. So no phase shift for sine, and that's why I'm using sine function. If it didn't start at the equation of the axis, I would probably use a cosine function and shift it to where the closest max or min is. So no phase shift if a sine function. So the next thing I'm going to do here is I'm going to recognize what the k value is. And we said that the k value is equal to 360 over the period. Well, the period is 0.25. It's a very small period. So if you divide 360 by 0.25, you're really multiplying it by 4. You end up with 1,440. We have our k value. We have our d value. It's 0. There's no phase shift. We have our c value is 0. And now we can also conclude that the a value, not just the absolute value, but it's going to be positive 10. And that's because it's a positive sine function if there's no phase shift. So we can put all this together. So the equation we get is y equals, the a value is 10. The sine of k is going to be 1440 times x minus 0. So we don't need to put anything in brackets. You just write an x there. And then we're going to add 0 to that. We don't really need to write the plus 0. But that is the equation where x is the time in seconds, and y is the distance from the rest position in centimeters. There you go. That's how you put that first part together. Now let's look at a second part to this question. So part B of this is representing this as a cosine function. So there's the graph I drew. There's my sine equation that I had. So if I was to represent that as a cosine function, you'll notice here that I'd have to shift it over to the closest max or min, and the max here would be right there. Now that would be a quarter of a quarter. A quarter of a quarter is 1/16. So remember, this is 1 quarter, 0.25. And so that would mean 1/16 is there, 1/8 is there, and then 3/16 would be there if you broke that up into quarters. And so 1/16 would be how much you've shifted it over. So that means your d value is 1/16. And it means your c value, that's going to be the same. C is still 0. The k value is still 1440. The period hasn't changed. And the amplitude is still 10. But it's positive. It's positive since we're starting at a max. If instead we had shifted it over to this point, which is a minimum, then we'd be starting at a minimum. So that would give me another situation. I could have d equals 3/16 if I went to the minimum. But then in that case, you'd have c and k being the same, but you'd actually have the a value that would be negative because of that minimum. And so if we were to graph it with the 1/16, if we were to write the equation for that, we'd get this. We'd get 10 times cosine 1440 x minus 1/16. You could also write that as a decimal. That would be fine to do that. And then plus 0, so you don't need to write the plus 0. And then if you did it with the shift of 3/16 down to the minimum, you'd have negative 10 cosine 1440, and then that would be x minus 3/16 degrees. And so both of those are the same graph. They both give you the equation that represents the exact same graph. In fact, all three of them do. The one we did for sine and now those two for cosine as well. The one last thing we're going to ask about this, and then we'll be done. So this last part asks this. If the wind speed decreases slightly, decreasing the sway by 20%, What is the new equation of the sinusoidal function? We have the three different functions we've written, which all represent that same graph. And so let's see if we can get the new equation first for sine and then for the two cosine options as well. The first thing to note is if the sway is reduced by 20%, normally the amplitude is equal to 10. And so what that means is that if we take 20% off, in other words, it's 80% of the amplitude. And so that means that the new amplitude is going to be equal to 8. Now, you might think, well, doesn't the period change or other things like that? Well, one interesting thing is that if you take a piece of metal and we push it to one side, we bend it to one side and it bends like so, it's going to spring back to the other side, and it's going to be, basically the more you push it, the more tension is going to be in the pole. If you push it less distance, so if we take that and we push it less distance, there's going to be less tension in the pole. In other words, it's going to spring away faster when there's a greater distance, so this is the 10 centimeter case, and it's going to spring away slower when it's in the lesser distance, the 8 centimeter case. So as it's springing off in that 8 centimeter case, going to each side, it's going to spring off slower, meaning that the time it takes to complete the cycle is going to be the same, regardless of whether or not the amplitude is 10 or 8. Same with a swing. If you're ever on a swing and you start pumping and going really high, start going really low, and you'll notice that it takes you about the same amount of time to go back and forth when you're low on a swing as opposed to if you're really high. So the time isn't going to be affected, therefore the period is not going to be affected or anything like that. The only thing that's going to be affected is the amplitude. So our new equation is going to be y equals 8 sine 1440 x degrees. Now you could also write that with the positive cosine. That would be 8 cosine 1440 x minus 1/16. Again, you could write that 1/16 as a decimal. Or if you use the negative cosine case, you could write that as negative 8 cosine 1440 x minus 3/16 degrees. So there you go. That's how you would write that new equation if you did a sine or a positive or negative cosine function. Hope that was helpful. If it was, feel free to give it a like and please consider subscribing. Thanks.